Hey, good morning, guys. Today we're going to be talking about congruent chords. So this is our second video within our unit about circles. If you didn't check out 8.1, make sure that you guys do check out that video whenever you have a chance to. Make sure that you understand the basics before we jump into chords. Now, to get started, yesterday we did talk about some information about chords that we need to recap before we actually know what we're going to be doing today. So, to begin, the definition of a chord. A chord of a circle is a segment joining any 2 points of a circle. Now, some important things here, those 2 points, they must be on the circle itself. And again, the chord is the segment that connects the two. So segment AB is the chord here. And this leads us to the question, is a diameter a chord? Well, yes, a diameter is a chord. In fact, a diameter is the longest chord within a circle. Because again, a chord is any 2 points on the circle. A diameter does span across the circle itself, and it goes at the most wide portion of the circle. So yes, the diameter is a chord, and in fact, it's the longest chord. Now, yesterday when we were talking about circles in our 8.1 video, we had a couple properties, and these are the properties of chords. These are what we're going to be using today. So the first property that we had stated if a radius, so we have radius, and I can draw my radius in here, xy. If a radius is perpendicular to a chord, then it bisects the chord. So I have chord AB, and I'm drawing that my radius and my chord are perpendicular. They intersect at 90 degrees. If that happens, if you see a chord and a radius intersect at 90 degrees, then the chord is being bisected. So that would cut the chord perfectly in half. So that AZ is congruent to ZB. The other property that we learned is just the converse of that. It states, if a radius of a circle, so in this case we have radius TR, bisects a chord that is not a diameter. So here's my chord, it's being bisected. It's congruent on both sides. Whoops, sorry, I need to bring everything back up. Sorry about that. Let me just go through this real quick once again. So if a radius of a circle bisects a chord that is not a diameter, so again, it can't be a diameter here because it wouldn't make sense if it's the diameter, then it is perpendicular to that chord. So if you see a chord that is being cut perfectly in half, then you can go ahead and draw a right angle there, which will open up a lot of possibilities. Now, typically when you're using these properties of chords, you're going to be using Pythagorean's theorem with it, but also the right angle opens up right triangle trig to use as well if needed. But again, that will open up a lot of possibilities here. So again, anytime that you see a radius being drawn through a chord, it's going to be perpendicular and bisect that chord. Oftentimes, they're going to use Pythagorean's theorem, being a squared plus b squared equals c squared, after you set this up. Now, that's just review. What's new today is these next theorems. The first theorem states, if 2 chords of a circle are equidistant from the center, then they are congruent. So I can go ahead and draw my 2 chords, chord AB and chord CD. And I'm going to go ahead and say that these 2 chords are equidistant from the center of my circle. Equidistant just means equal distances. So therefore they're congruent. They're the same distance apart. If you see this occurring, if you see that we have 2 chords and they're the same distance from the center, then they, meaning the two chords are congruent. So AB would be congruent to DC. So again, if you see congruent chords, they are equidistant from the center of our circle. The converse is also true. If I have 2 chords of a circle, and I'm going to draw this one a little bit differently, where they share a common endpoint on our circle. That way you guys can see various methods of this. If 2 chords of a circle are congruent, so we already know that these 2 are congruent, BA is congruent to AY. So if you see that they're congruent, then I can go ahead and draw the center of my circle, and both of those chords will be the same distance from that center. So both chords would be the same distance from point S here. So therefore, this purple segment is congruent to this purple segment. Now, those are the properties that we'll be using in order to solve the coming problems. Again, we have our properties that we just talked about on the previous slide, and we have our theorems here. And this is all we really need in order to solve problems with chords. So let's go ahead and get started with a sample problem. It says, given circle O, so we can see that we have circle O, O is the center here. We're given that segment AB, which is a chord, is congruent to segment CD, which is also a chord. We're given that OP is equal to 12x minus 5, OQ is equal to 4x plus 19, and we'd like to solve for OP. Now, think about what we can do in order to solve this. Okay, so we're given two chords, and those chords are congruent. Based upon the last theorem that we just talked about, if the chords of a circle are congruent, then they are equidistant from the center. So therefore, PO and OQ are going to be congruent. Well, if two things are congruent, that means that they are the same. And if they are the same, then I can set them equal to each other. So 12x minus 5 equals 4x plus 19. If I solve for x, will that allow me to solve for OP, our end goal? Well, OP is 12x minus 5, so yes, if I can solve for x, then I can solve for OP. Solving for x, I'm going to subtract 4x from both sides and add 5 to both sides. That will leave me with 8x equals 24. From here, I want to get x isolated, so I divide both sides by 8, leaving us with x equals positive 3. Now, if I want to solve for OP, I just need to plug it back in. It won't really matter which one you plug it into because they're congruent, but again, I just want to make sure, so I'll plug it into OP. That'll give me 12 times 3 minus 5. 12 times 3 is 36. 36 minus 5 is 31. So our final answer for the segment OP is 31 units. Next up, given circle O, and this time we know that OB, the radius, is perpendicular to PQ, the chord. We're given that BC is 5, that PQ is 30. We would like to find the radius of circle O. So to get started, I'm just going to go ahead and draw what we have here. And since these are perpendicular, the radius and the chord, that would mean that the chord is being bisected. And if the chord is equal to 30 units, that means that PC is 15 and CQ is also 15. Further, I know that BC is 5, but we want to find the radius. So what if I call OC x? Well, then our radius would just be x plus 5. So let's go ahead and do that, and we can set up a right triangle here. So I know that OC is x. I know that our radius is x plus 5. So OQ is x plus 5. That will allow us to solve for a right triangle. So now we have x squared plus 15 squared equals x plus 5 squared. Now when I have x plus 5 squared, that's the same as x plus 5 times x plus 5. So you'll have to use the FOIL method or double distribution, whichever one that you're more comfortable with. Same thing though. Where I distribute through fully, give me x squared plus 5x. Then I distribute my second term fully, giving me 5x plus 25. That will in turn give me, well, let's go ahead and just work through this now. X squared I can bring down. 15 squared is 225. And then x plus 5 squared will turn into x squared plus 10x plus 25. All I did was I combined my like terms here. From here, I'm going to go ahead and get all of my terms on the same side. I'm going to go ahead and start solving. So I'm going to subtract x squared from both sides, canceling out the x squareds. And subtract 25 from both sides, leaving me with 200 equals 10x. Lastly, I divide both sides by 10, leaving me with x equals 20. But again, I don't want x. I want the radius. The radius is x plus 5. So therefore, the radius of circle O is going to be 20 plus 5, or 25 units. All right, next up, let's go ahead and try out a proof. Given triangle ABC is isosceles with base AC, we're also given circle P with PQ being perpendicular to AB and PR being perpendicular to CB. We'd like to prove that the small triangle in the center, triangle PQR, is isosceles. So to get started here, first off, we should take note that AC, CB, and AB, all sides of this triangle, are chords. And further, they tell us that triangle ABC is isosceles with base AC. So of course we start this off with our given information. And then from here, I'm going to go ahead and take the obvious answer. I'm going to take the isosceles triangle, and I'm going to further our proof based upon that. So since this is an isosceles triangle, I know that AB is congruent to CB. The reason I can say that is an isosceles triangle has at least two congruent sides. That's the definition of an isosceles triangle. Now that we know that the chords are congruent, well, we have a theorem for that. If the chords of a triangle are if the chords of a circle are congruent, then they are equidistant from the center. So that would mean that PQ is congruent to PR. Because if two chords are congruent, which we have from statement number 2, then the chords are equidistant to the center. Well, look at this. I have a triangle, and we have at least two congruent sides. That must mean that triangle PQR is isosceles. Because by definition of isosceles that we talked about earlier, a triangle with at least two congruent sides is isosceles by definition. And with that, this proof is complete. All right, let's go ahead and try out our final question. This is a challenge question, so just be prepared for it. We're given triangle ABC, which is isosceles, with AB being congruent to AC. Those are the congruent sides. We're also given circle E. Within circle E, we have AD, which is perpendicular to BC, and then we have EF, which is perpendicular to AC. So to get started on this, we also have that AF is 6, ED is 1. So to begin, I'm just going to go ahead and draw in the information that I have. Now, from here, since EF is perpendicular to AC, that would mean that FC is also 6, and that the whole entire side of AB is 12. Further, I know that AE is a radius, so I can call that R. And then EC is also a radius. I'll also call that R. So what you can see happening here is that we're seeing a lot of right triangles occurring. So with that, I'm going to go ahead and use that information to help out with the proof. So let me go ahead and draw in some more information. I'm just going to go ahead and make this a little bit nicer. Okay, so now that we have this, we're going to go ahead and focus in on this small purple triangle. I'm going to use this purple triangle, triangle EDC. And I'm going to use our large triangle over here, triangle ADB. So those are the two triangles I'll use. So using this small triangle, I'm going to set up Pythagorean's theorem. That would give me y squared plus 1 squared equals r squared. Solving for y squared, I'll be left with y squared equals r squared minus 1 squared. Of course, 1 squared is just 1, so I can just leave that as 1 instead. Next, I'm going to go over to my bigger triangle, triangle ADB, and do the same thing. I'm going to set up Pythagorean's theorem. So I'll have y squared plus 1 plus r squared equals 12 squared. Again, I solve for y squared, giving me 144 minus r plus 1 squared. Now let me go ahead and do a little bit of math with this negative r plus 1 squared. That's the same as negative times r plus 1 times r plus 1. Again, if I FOIL, I'm left with negative times r squared plus r plus r plus 1. Again, that's just FOILing, first outside, inside, last. Combining like terms will give me negative times r squared plus 2r plus 1. And distributing the negative through gives me negative r squared minus 2r minus 1. So again, this chunk right up here, negative r plus 1 squared, is the same as negative r squared minus 2r minus 1. So at this point, I can see that they're both set equal to y squared. If two things are equal to the same thing, then they're equal to each other. So I'm going to go ahead and use substitution, set them equal to each other. That'll give me 144 minus r squared minus 2r minus 1 equals r squared minus 1. Let me go ahead and get rid of this since we saw where the work came from. And from here, we can go ahead and further this proof. Or question, I guess. So at this point, I'm going to go ahead and get everything on one side of my equation. So I'm going to subtract r squared. I'm going to add 1. And what that will give us is it'll give us negative 2r squared minus 2r plus 144 equals 0. Now, as you can see, I put this in standard form. Ax squared plus bx plus c equals 0. From here, I factor. I see that I have a GCF. These are all even numbers. So my GCF is negative 2. I factor out a negative 2, leaving me with negative 2 times r squared plus r minus 72. From here, I look for numbers that add to be our middle term, 1, right, the number in front, and multiply to be negative 72. Numbers that multiply to be negative 72 are all listed here. And of course, I also have the opposites on the other side. But out of all these pairs, which ones add to be positive 1? Well, the only one that adds to be positive 1 is negative 8 and positive 9. So I put those in my double bubbles. So I have r minus 8 times r plus 9 equals 0. At this point, each bubble gets its own equation. R minus 8 equals 0, r plus 9 equals 0. Solving for each, we're left with r equals 8 and r equals negative 9. But I can't have two different radii within the same circle. It doesn't make sense. Which one makes more sense for this problem? A radius of positive 8 or a radius of negative 9? Well, a radius is a distance. And I can't have negative distances, so our correct answer is r equals 8. So we're going to keep that for letter A. The radius is 8. Now I need to solve for y so I can find the perimeter. I already have two sides of my triangle. I have 12 and 12. I just need this bottom side. Now I already solved for r, so if I plug that back in, I should be able to solve for y. I'm going to go ahead and plug it into the purple triangle. I'll make it a little bit easier. Could I plug it into this other triangle? Absolutely, just more work. So plugging it into our purple equation here, I'm left with y squared equals 8 squared minus 1. 8 squared is 64. 1 squared is 1. 64 minus 1 is 63. Y squared equals 63. If I want to get rid of the square, I take the square root of both sides. The square root of 63 is 3 radical 7. Of course, since BC, the whole thing, is 2y, well then I'd have to multiply 3 radical 7 by 2 to get the entire length. So therefore BC is 6 radical 7, which would make our perimeter 12 plus 12, which is 24, plus 6 rad 7. And that would be our final answer. 24 plus 6 rad 7 is our answer for letter B. If you need a decimal, plug it into your calculator. And then 8 is our answer for letter A. Again, this is a challenge problem. Chances are you guys won't see one like this in the future, but I do want to challenge you guys when given the opportunity. Thank you guys so much for watching today. If you have any questions, please let me know. But other than that, have a